Students, last video we have seen moving coil galvanometer and we have found out the expression for the deflection produced phi is equal to NAB upon K into I, and we showed that the deflection produced in the moving coil galvanometer is directly proportional to the current passed through it. If the current passed through the galvanometer is more, then the deflection will be more, and similarly if the deflection will be less if current passed through the coil is less. Coil means moving coil galvanometer coil. We have seen this point. I hope you have gone through that point, 238 page number. Now we shall see the next point, that is magnetic dipole moment. In 11th standard we have seen something about magnetic dipole moment. We had a figure in which a circular coil, current carrying coil was there, having a single turn. If the current is anti-clockwise sense, then that surface was acting as a N pole, and if the current is in clockwise sense, then that surface of the coil was acting as a south pole. And the direction of magnetic dipole moment for such current carrying coil is from साऊथ टू म्हणजे आपण इथं मॅग्नेटिक डायपोल मोमेंटची जी दिशा घेतो, ही मॅग्नेटिक डायपोल मोमेंटची दिशा कशी असेल बघा. द करंट कॅरिंग कॉइल इज इन दिस वे, द करंट कॅरिंग कॉइल इज इन दिस वे. सो दिस इज द मॅग्नेटिक इंडक्शन. सो यू हॅव टू होल्ड दिस करंट कॅरिंग कॉइल in the right hand. If the thumb shows the direction of current flowing through the coil, then the curved finger shows the direction of magnetic induction. So here we can see that this surface acts as north surface. So from south to north, here you can show the magnetic moment. Direction of magnetic moment is perpendicular to this plane of the coil and towards us. And if it is a anti-clockwise sense, it is clockwise sense, then the direction of magnetic induction will be inside. Direction of magnetic induction will be inside, and we show it to be by cross. So here this acts as a N pole and this acts as S pole, that we have already seen. And the direction of magnetic dipole moment will be from S pole to N pole inside the magnet. So here if it is N pole and this is S pole, then this is the direction of magnetic dipole moment. Magnetic dipole moment is a vector quantity and we have defined it as m into 2l. This is we have done in 11th standard. Magnetic dipole moment is the product of magnetic pole strength of one of the poles of the bar magnet and the distance between the two poles, that is S pole and N pole. This distance was taken as 2l. So this is the basic thing that we have seen already in 11th standard. Now in this case, instead of capital M, in your book they have used a letter mu for showing the magnetic dipole moment. For showing the magnetic dipole moment, they have used the letter mu. Instead of capital M, they have just used the notation mu. And mu is equal to, and the magnitude of mu is equal to NIA. This also we have seen in 11th standard. So mu is equal to NIA. N is the number of turns of the coil, I is current flowing through the coil, A is area of the coil. Suppose we have a coil passing the current in anti-clockwise sense like this, and this coil is having n number of turns, and A is area of coil. A is equal to pi r square will be the area of coil, because r is the radius of the coil. So coil is circular, so area formula will be pi r square. So NIA, suppose mu is equal to NIA, this is the magnetic dipole moment. Now magnetic dipole moment will be in the direction of perpendicular to plane of the coil, and whether the current is clockwise or anti-clockwise, depending upon that we have decided the direction. Now the direction of mu is in the direction of n cap. What is n cap? N cap is a vector which is perpendicular to plane of the coil, which we have studied in the last point, that is torque acting on the current loop. N cap was in a direction perpendicular to plane of the rectangular coil kept in uniform magnetic field. युनिफॉर्म मॅग्नेटिक फील्डमध्ये करंट कॅरिंग कॉईल आपण रेक्टँग्युलर ठेवली होती. एन कॅप हा त्याला परपेंडिक्युलर असतो. त्याच डायरेक्शनमध्ये म्यूची डायरेक्शन असते. म्यू म्हणजे मॅग्नेटिक डायपोल मोमेंट असतो, हे लक्षात ठेवा. सो म्यू इज इक्वल टू NIA. आता समजा आपण जर एखादी कॉईल युनिफॉर्म मॅग्नेटिक फील्डमध्ये हेल्ड केली. इफ वी हेल्ड ए कॉईल हॅविंग n number of turns in a uniform magnetic field of induction B, then the formula for torque is equal to NIAB sin theta, which we have already proved. हे आपण प्रूव्ह केलेलं आहे, NIAB sin theta. But what is NIA? NIA is mu into B sin theta. So NIA is equal to mu. So torque comes out to be mu cross B. सो टॉर्कचा फॉर्म्युला काय येतो बघा, म्यू क्रॉस बी. असा सुद्धा फॉर्म्युला आपण टॉर्कचा काढू शकतो. इलेक्ट्रिक डायपोल जेव्हा आपण इलेक्ट्रिक फील्डमध्ये ठेवलेलं असतं, अकरावीमध्ये आपण शिकलोय की मैंने इलेक्ट्रिक डायपोल इज केप्ट इन युनिफॉर्म इलेक्ट्रिक फील्ड. सपोज दिस इज अ युनिफॉर्म इलेक्ट्रिक फील्ड and an electric dipole is kept in such a electric field, then it experiences a torque, and that torque is equal to P cross E, where P is the electric dipole moment of the electric dipole and E is the electric field. So we have got here two similar equations. Two analogous equations. When torque is acting on a coil carrying current kept in external magnetic field, uniform magnetic field, then the torque formula is mu cross B. And when an electric dipole is kept in external uniform electric field, the torque experienced by that dipole will be P cross E. So we have got two similar formulae here. Okay, so please take into consideration these are the two formulae which are analogous. One is for a current carrying coil kept in external uniform magnetic field, and another is electric dipole kept in external uniform electric field. Okay, so these are the two similar equations. The next video I am going to explain magnetic potential energy. So magnetic potential energy, the concept of magnetic potential energy we are going to study now. Okay, in the next video I am going to give it.